Next speaker is Rachel Breslin. Rachel is a chartered civil engineer with the Institute of Civil Engineers with 13 years of experience in structural engineering, project management across the oil, gas, transportation and offshore wind sectors. She is the principal project manager at Kent Energy, who are a global leader in energy solutions, where she spent the last 3 years contributing to the advancement of offshore wind projects. And prior to that, Rachel spent over a decade at Atkins Consulting Engineers, specializing in structural engineering and project management in the energy sector. So I'll hand you over to Rachel and we'll take your questions afterwards. Thanks, Rachel.
Yeah, as Pat said, I'm a principal project manager with Kent Energy, which used to be actually part of Offshore Energy with Atkins. So that's why not many people know of us. But yeah, I'm just going to talk to you through today mainly about the offshore wind sector in the UK and Ireland, but kind of a bit of an overview first of kind of what a wind farm is, the global offshore market, and then towards the end a bit more into the detail of actually what I do on a day-to-day basis and kind of the challenges around kind of the design and delivery of our projects. Okay, so I thought, yeah, first off, I might just paint the picture a bit of what is an offshore wind farm. I'm sure most of you are aware of it and what they are, particularly in the current market. But yeah, here we have, it mainly consists of a slight layout of wind turbines. They're usually interconnected, and you usually will have you can have multiple substations. It really depends on the size of the wind farm offshore, which then connect into an onshore substation, which is then distributes the energy to the end users. So kind of the main components of, I suppose, when we look at an offshore wind site, it varies. So this is actually one that what I do on my day-to-day basis. We design the substructures for these for the wind turbines. So you can see here there's a variety of different types of substructures, and very much depends on how deep the water is, kind of what substructure you use. So you can see here, these are what we deem as floating structures, so semi-subs, spars, which are usually anchored to the seabed. That's usually in water stacked up over 100 meters. Kind of under 100 meters, we look at what we deem as a jacket structure. So this is quite commonly seen in the oil and gas market. What a lot of the platforms would be used to construct them. This is a substation which also a lot of them would use a jacket structure. And then as you get shallower, you go into the depths like monopiles, which are basically just a big tube, and then some gravity-based structures. So it very much depends on the water depth, soil conditions of what type of structure you use. And so for that, and then kind of coming on to a wind farm layout, kind of how you set out your wind farm depends on a number of factors: how many turbines, the water depth, soil conditions. Turbine sizes are getting bigger and bigger. So at the moment, we're looking at 15 megawatt, 20 megawatt turbines. A lot of them, 20 megawatts, just say they're nearly spaced a kilometre apart. So that just gives you, the size of them, and you can have something up to 100 plus wind turbines on some of the sites at the moment. So it's a huge area. So kind of looking into that, they look at, so many turbines will need a substation, to look at substation positioning, cable array layout, and a lot of that input then is to do a lot of surveys that will need to go into kind of, I suppose, finalize the type of substructure we use, and the final layout, and a lot of that is at the very start is trial and error, and a lot of concept and different solutions to see what the best fit is, and obviously that aligns with capex, opex, and what I suppose the developer is looking to get out of it. So just to give kind of I thought it'd be useful to give a breakdown of kind of the costs of a wind farm. So this is just the capex, so the capital costs here. And you can see, you know, a major part of this is actually the turbine cost. And I think, you know, that makes sense to a lot of people, a lot of that turbine as well. And obviously the upfront cost, but also the operational costs and the maintenance of the turbines. You then have a lot of the substructure and foundations. So yeah, that's obviously all that steel, all those jackets, piles, whatever the substructure is. It's a lot of steel, and that fabrication costs and installation as well, you can see here, is quite high. Similar, like when you go into the LCOE, which is the levelized cost of energy, and that kind of looks at what is the average cost of producing electricity over the lifetime of the wind farm. And again, you can see here, you know, the turbines is a major factor in that, and along with kind of the substructures and foundations. Most of these wind farms are designed for a 25-year lifespan. Obviously, as they come closer to that end of life, there's looked at, you know, structural optimization. What can we do to further, you know, extend the life of them? There's a number of offshore wind farms already that are coming to that stage, actually already within the UK, which is quite interesting. So we're already kind of looking at life extension and what we can do. And I suppose a lot of that experience comes from the oil and gas market, where they've been extending the platform life for the last 50 years or so. Okay, so just, yeah, quick, I think we showed there kind of about turbines, but yeah, the main turbine players, I would say at the moment are kind of, you have Vestas, Siemens Gamesa and GE. So at the moment, Seagreen wind farm was one which was installed this year. They're using a 10 megawatt turbine. We're currently designing for a 15 megawatt turbine. So just to give you an idea, 50 megawatt turbine, one at the blade length is 115 meters. And they're just getting bigger and bigger. So we're already being asked to design for 18 megawatt, 20 megawatt, 22. I think at one stage we had someone ask us if we could design for 28. And just to get an idea, these aren't even they're not even being fabrication of mass. Yeah, so, and there is a bit of an argument at the moment, you know, where do you stop? You know, you're looking at vessel capability and installation, you know, how do you transport these and install them? And there is talk that, you know, will a max out of 50 megawatt, is that the best place, you know, to optimize it and to actually create the capacity and, you know, the procurement process for that and the installation capabilities. So yeah, it's also known a single rotation of a 50 megawatt turbine, I think, can generate enough electricity to power a typical UK home for 2 days. So that's just one rotation of one of these turbines. And a lot of the, particularly in the UK, when actually the project I'm working on at the moment is going to be over 100 turbines. So that's you know, it's overall that wind farm is going to be 4 gigawatts in total capacity. To give a comparison, Hinkley Sizewell C is 3.2 gigawatts. So, you know, we all probably know how long Hinkley has been going on for. So if you think of, at the moment, the project I'm working on, we're in the detailed design stage, it's placed to be operating by 2030. So, you know, it kind of just shows you kind of the fast turnaround of design and getting it installed, fabrication and installed. Okay, so yeah, I thought it'd be useful as well just to give a bit around the global kind of offshore wind market first. So this is a graph, it's from the offshore wind market report that was for 24. So it's a lot of it's based off 23 information. But I think it's quite an interesting kind of graph in terms of where we're supposed to be by, or the plan is by 2029. So that's 193 gigawatts of energy. So as you can see, exponentially is to grow. I have a slide and next, currently we're at 68. So that's nearly triple, you know, the capacity within the next, 4 years. So that is, it's a big target. Is the market there? Is the procurement process there? And I think that's the big challenge is, you know, it's that backlog of, you know, the installators, the fabricators, and people to actually be able to construct and install these foundations and wind farms. So most of the world's operational offshore wind capacity is installed on fixed bottom substructures, as I kind of showed you before this. So floating technologies are advancing, but they're still kind of very much in their infancy. But the technologies there is advancing more and more, and the hope is that, yeah, and particularly in those deep water areas, that floating wind farms will become more prevalent. So you can see here, this is this is the 68 gigawatts I was talking about. So it's nearly all monopiles, which is just basically a big cylinder, is the preferred. That kind of makes sense. It can be done in shallower water, less steel, so it's a bit cheaper. I don't know if from Brighton you can see Rampion. Out from Brighton, that's all monopiles. So that's kind of a good example. And kind of more the, I suppose, jacket structures. There's a lot done off both the north coast of England and into Scotland. Suction bucket jackets, they're quite new. That sea green was installed using suction buckets, so they're another way instead of using piles, which deals with kind of if you have difficult soil conditions as well, or well, you kind of need the right soil for them, but it's quite an interesting solution as well for instead of having to use piles and to drive our drilling right. And then I suppose going over here to kind of the proposed for future projects, we're looking at another 72 gigawatts of global capacity of development as well. So again, the majority here is monopile, but you can see here the floating is growing, and that's proposed, and that's potentially because of that development of that technology and its advancements. At the moment, it's quite expensive compared to fixed bottom substructures, but I think the hope is that it becomes more and more efficient over time. I thought it'd be useful to kind of just give some recent trends. So I think when you think of all these numbers sound really big, and particularly at the start when I showed that slide of 193 gigawatts by 2029, which seems quite ambitious, but in the grand scheme of things, they're saying like to achieve the Paris Agreement to reduce the 1.5 degree global warming, the world needs 8,000 gigawatts by 2050. So very much it's really only a small part in the bigger picture. I think you can see already it's grown. The operating capacity of offshore wind has grown 10.2% between 2003 and 2002. And offshore wind, the target is 380 gigawatts by 2030, which again seems very, very ambitious, and 2,000 by 2050. So I think all these targets are quite ambitious, particularly if you kind of look at the supply chain and the limitations there, and what can be met. But I suppose these are the challenges we're trying to address. Kind of going on and breaking this down a wee bit more into which I think is a bit interesting to look at kind of the different markets and where the future capacity is going to be. The US potentially might change with the change there, but that there was a lot of offshore wind coming from the US in the last development a few years ago. Now that may pause, so I suppose there'll be other markets, but Ireland is a big one. Germany, the Netherlands, and Taiwan and Japan are already have some of the biggest farms, particularly Taiwan. Have a lot of wind farms already and capacity there. Going on kind of further, 2030, you can see kind of Colombia, Brazil, huge potential there again. Turkey, India. The Australian market, we can already see they're doing a lot. They've done a lot of their leasing rounds recently, actually. So that's starting to pick up momentum, and there's a lot of kind of start the work there going on in terms of optioneering and looking at different solutions for particularly off the Victoria coast. So that's already work we're kind of seeing at the moment kind of come true. And then when you look at 2050 again, I think Brazil again is a big one here. South Africa and Egypt. There's some countries which are probably, particularly in that Middle East section, like somewhere like Egypt and India and Turkey, a lot of fabrication yards around there. So they're actually positioned quite well in terms of being close to the fabricators. Azerbaijan is another one, Sri Lanka. As I'll talk about kind of towards the end, a lot of the structures are being actually fabricated in the Middle East and Asia and China. So if you think they're being fabricated one part of the world and then transported to Europe, which in a way kind of argues like, you know, it's renewable energy. Are we using a lot of fossil fuels to get them installed, rather than is there a market there for, you know, developing the skill set here, which there used to be since oil and gas. But a lot of it is about that cost, and the cost of labor and the cost of steel is cheaper. And that's kind of the driving force at the moment. Yeah, I think, yeah, pretty much similar countries I discussed it in 2050. So all in all, you know, there is a lot of potential, but I think it's really about unlocking this. And as we'll discuss, it's not a straightforward process. I'm going to discuss a bit about the UK and our Irish markets, but getting all that set up in all these countries and unlocking all that potential is challenging, and it really needs kind of the government and to be behind of each country to be behind it and drive it forward. Okay, so before we kind of go into discuss about kind of the UK and Ireland specifically, I thought it'd be useful just to get an idea of kind of the project development stages. So yeah, you can see here kind of, sorry, the color isn't the best on the screen, but you have seabed leasing rounds. This is where it depends what government or what agency they kind of go out and they sell, they lease portions of the seabed for around 15 years. Then you have kind of applications for lease and the consent process and development. So this is where once a developer, just say such as SSE, Ørsted, BP, they might get that area of land, they do their surveys, and they start looking at the design, what the optimum design would be, what kind of structure to use, what kind of turbine to use. Then they'll start getting, like any kind of project, it needs to go through consent, and it needs to have an environmental assessment done, and then you're kind of going into that consent process. Kind of after the consent process and when planning permission is granted, you have what's called, it's nearly another auction round, which I'll discuss a bit later, and then you have something called a contract for difference, which I will actually, I'm going to discuss a bit more, which is kind of the funding really behind it. And then you're looking into pre-construction, construction, and then operation. These are kind of more at the bottom, the design cycles. So yeah, kind of like already kind of cover them high level, but you have concept, feed, detailed design, and then yeah, your procurement, fabrication, and construction and consenting. So some of these do need to be done in parallel. I won't talk about these anymore here because I'm going to discuss about them in a bit more detail towards the end. This is an indicative kind of timeline of how long the projects last. As I said, a lot of these projects they're a 25-year design life. So kind of the start, you know, is around between the consenting, design, the leasing process, fabrication, construction, you're looking around 10 years, 25-year life. Then potentially that life extension. It's hard to determine at the moment how far these foundations will be able to their life be able to extend it, because I think one of the big challenges we have is to make them as light as possible, so that, you know, that means their end life or how much they can be extended by maybe not the same as what we see with the oil and gas platforms, which were designed kind of in the 70s, 80s, and were probably over designed. So it'll be interesting to see kind of how much further we can get out of the structures. But part of that is also the turbines and their lifespan as well. Okay, so going on to a bit about the offshore wind market in the UK. So yeah, the UK is really it's one of the biggest offshore wind players in the world. Already it has 50 gigawatts of offshore capacity target by 2030. Currently has 14 gigawatts of operation capacity. It plays around, at the moment, I think it's around 20 to 30% in the overall market in the world. So it is a lot of experience, a big player. So that kind of, I quickly run through the lifestyle and life cycle prior to this, and how it works in the UK is the Crown Estate is the body that manages the marine assets, which are owned by the sovereign. So they control and they're administered by the government. So these assets include any seabed out to 12 nautical miles, most of the coastline around the UK. And then you have the Crown Estate, which deals with Wales and England, and then you have the Crown Estate Scotland to manage the seabed leasing for Scotland. So before consenting can begin, the developer, as I mentioned, needs to secure a lease of one of these sites off the coast or whatever area. So previously there was leasing around 5, I think, which was the Celtic Sea area. So there were the areas. So that's where the developers will I suppose bid for this area. So and then once they win it, they kind of go off and start looking at kind of the wind farm layout, what can be done there and what can be installed. And they, along with that, will be lead up to the consenting process. And then as per the consenting process, it's obviously England, Wales, and then Scotland, and then Northern Ireland is slightly different again. And then all that is then and goes through that process. So I mentioned previously contract for difference. So once planning application is agreed, there kind of goes into another mechanism of auction rounds. So this year it's last year we had auction round 6. Previous to that we had auction round 5. So apart from this auction round, the government set it's called contract for difference, and they set what it's a strike price. So it's a price of what they're willing to agree the electricity to cost. So that kind of works out if the market price for electricity is lower than the strike price, the government, the developer is paid back, and if the market price is higher than the strike price, the developer needs to pay that difference back. So it's a kind of a win-win solution, or a pain gain, really. So it's really this mechanism for supporting low carbon electricity, and it's to really incentivize developers that, I think we all know the energy market can be quite volatile, and there can be increases or decreases. So this really kind of, I suppose, gives them some certainty and they know what they get. In terms of seal bid, so a strike price, I'll go to my next slide because it shows a strike price is set, and the developers basically need to submit a price that's that price or below it. So it's it's a competitive process. So they'll all be going in trying to be as competitive as possible. So this is where they're looking at this. They determine the strike price by looking at how much it's going to cost to develop the wind farm, and how much and as competitively as possible go in there to win. They can be a number of times. There is only so many contracts of difference that are awarded. So sometimes there is a number of developers that on offshore wind projects that might not be developed because their strike price might be too high and not competitive enough. So yeah, the contracts are usually paid a flat rate for 15 years, and then it goes into kind of negotiations after that. There are other ways to kind of routes to market, but it's a lot to do with developers and getting backers behind them. But this is, I suppose, the most secure way for a lot of developers to kind of get that financial backing to actually be able to go and construct the wind farms. So yeah, as I mentioned, so 6 auctions so far, and round to date plus Scotland. Actually, it's worth noting that Offshore Wind 5 failed to forward any offshore wind projects. So it was deemed then the strike price was quite low at that time. So it meant that basically none of the offshore wind, it wasn't affordable for them to construct these wind farms with that price. So for AR6 actually saw the strike price increase for the first time. So the capital cost of wind farms and actually designing, constructing them has reduced dramatically for the last few years. But then in the last few years, obviously due to inflation increases, particularly procurement, supply chain becoming more difficult, the cost has increased. And that was reflected in AR6 when the actual strike price increased. So it made it a lot more favourable for a lot of developers to go forward than for that. I don't know if there anything. Yeah, so I have some numbers here. So the strike price for AR1 was 120 pounds per megawatt hour. Down in AR4 it dropped to 40 pounds per megawatt hour, and then last year for AR6 it was 57. So still a big change from AR1 to AR7, but AR6, but it just shows kind of how the market reflected by no offshore wind and AR5, just because it wasn't feasible for these developers because of the costs. Okay, moving on to kind of the offshore wind market in Ireland. So yeah, Ireland is kind of at the start of, I suppose, its offshore wind journey compared to the UK. The UK have been constructing offshore wind farms for 20 to 25 years, so they've a lot of experience. And I think this is where potentially, you know, Ireland can benefit from the experience of the UK as well. So Ireland's Climate Action Plan commits to achieving at least 5 gigawatts of installed offshore wind capacity by 2030. And that includes a further 2 gigawatts that's earmarked for the production of green hydrogen. And then you can see there up to 20 gigawatts by 2040 and 37 by 2050. Again, quite ambitious targets, but I think, you know, ones that are needed if we kind of want to see that switch from fossil fuels to renewables. So our offshore, so ORES, which is Offshore Renewable Energy, Renewable Electricity Support Scheme, it's kind of the equivalent of kind of the CFD scheme in the UK. It's slightly different. So ORES operates through competitive auction rounds where developers bid to receive a contract for generation electricity from offshore wind projects. So quite similar to what I discussed there in the UK. In May 2023 was the first round of the ORES one, so the first round of that auctions, which took 3 gigawatts of offshore wind capacity. ORES one was a developer-led. So you can see here the 4 wind farms there. There's 3 on the east coast and 1 off the coast of Galway, and that was actually led by the developers, and it was done in, I suppose, a bit more. They needed marine area consent before they could go to auction, so there was a lot more upfront costs, which was quite difficult, I suppose, for them, and to get those investors involved. As part of ORES 1, there was 2 applicants that weren't successful. They were Arklow and Oriel Wind Farm, but 2 again off the east coast. So at the moment, actually, I've seen today, I think Dublin Array is planning on putting in their planning permission in the next few days. So that's advancing. There has been some, I'm going to say, negative feedback from Ambod of how long they're taking in terms of getting this through. But again, I think that's a lot to do with, you know, this is the first round of kind of offshore wind farms in development, and, you know, there's a lot of policy, a lot of infrastructure that isn't there, and a lot of lessons that are being learned as we go through this. But I suppose very useful that a lot of the experienced people who are designing these wind farms are involved have done so in the UK. So useful in that sense. Sorry, this is click on. So that was where I discussed Arklow Bank 2 and Oriel. That's another 1.2 gigawatts. So I already talked about the contract for difference and the ORES, which, you know, which kind of is a government-backed scheme of being able to fund these offshore wind projects. But another way is this corporate power purchase agreement. It's a strong alternative that the developers can go to. It kind of gives them a certainty because it locks in a price for electricity, but gives a greater kind of flexibility than the government schemes if things are fluctuating, and allows to buy and sell a bit and to negotiate a bit better. but kind of obviously a bit more trickier to go ahead with, just because of getting those investments and the corporate backers. I'm going to go on next to talk about ORES 2, which is coming up, which is the next auction. I don't have, so this map here, which may not be very clear, is for ORES 2. So for between ORES 1 and ORES 2, it's a kind of a different approach being employed. So it's going to be actually plan-led, which is a bit more of a structured approach than the first one where it was developer-led. So this is Tonure site, which is off Waterford, which is going to give 900 megawatts capacity. So kind of how this works is it's basically an overarching framework. They've taken it from the EU and National Maritime Spatial Planning Policy. And then the first proposed one is the South Coast DMAP, which is Destination Maritime Area Plan. And it's basically to give a more structured way of bringing and developing wind farms in Ireland. So yeah, the first site is Tonure, and then the next one after that is Libon, which both are off Waterford. So it's more looking, rather than looking at different locations around the country, it's kind of set in areas. I think after this, it's kind of more the south coast, so around Cork, and then further up the west coast as well. So they're looking at different areas, so they're doing them in a planned sequence rather than just being scattered everywhere. As part of this, which is slightly different to the UK, the Irish government actually do a lot of the initial surveys. So before developers come in here, they're actually getting information, so they kind of know kind of the ground conditions, the depths of water, so they're getting information rather than having to pay a lot of that upfront cost themselves. So what you see sometimes in the UK, you see a lot of developers looking at the one site and they all go and do their own surveys, and that actually adds a lot of cost, where this is a more approach where the government is actually getting the surveys, and then when the auction process happens, the developer that wins or is successful will get that in, will be given that information. That information is freely available kind of as part of that, which again, it kind of encourages, and it's again not really, it's a bit more efficient and not as wasteful if you think of all these different companies going out and gathering that information. What else is on here? Yeah, so this so how this works, this kind of the DMAP sequence, it's so yeah, it's kind of looking, I suppose this is how they came out with the South Coast one, but it's looking at the areas, using maritime data, kind of doing a draft DMAP. Then they carry out, some environmental assessments, the impact of that. And then this DMAP is kind of drafted along with the environmental assessment reports. Public consultation is carried out, and then it kind of is approved. And then after that sequence is carried out, then the ORES 2 will happen. So where developers can bid for these for the leaseholds of these areas. Actually, the next slide kind of shows this a wee bit better. So you can see the DMAP there. So this is where there's a lot of consultation surveys done. And then the routes to market. So kind of the MAC, the marine area consent, and the routes to market happen at a similar time. So routes to market, which will be kind of the ORES, are through the CPPA. That's done, and similar, they need the developer will look at the area, develop it, the wind farm, the structures, and then they'll get a marine area consent. And that kind of goes into the grid offer as well. So that's all run actually by EirGrid. And I suppose what makes this the ORES 2 a bit different is EirGrid are actually developing, the network. They've looked at the site and they're developing the infrastructure for it, compared to the first ORES where the developers had to do all that work. So it's definitely more attractive for the developers coming into it. Yeah, so this is where you get routes to market, and then obviously the planning permission, and then it kind of goes into the construction phase. So yeah, that's quite a high level, quick overview of kind of the markets in Ireland and the UK. What I thought might be a bit more useful now is I'm kind of going to discuss a bit about the delivery of these offshore winds. So that was very high level, more kind of the overview. What we do on a day-to-day basis is we actually design the foundations. How a lot of these offshore wind farms work. We just discussed the program. We have all these packages. So you have foundations, turbines, cables, you have transportation installation, a number of different factors, and kind of what I focus on a day-to-day basis is actually the foundation packages. So they kind of vary from kind of the concept and field development, feed, which is front-end engineering design, which is pretty much like prelim design, and detail design, fabrication, transportation, installation, and operational. So we kind of deal with projects from this very concept stage where you're trying to decide what kind of foundation to use. Should you use a jacket? Should it be floating? And again, a lot of that is determined kind of by the soils, the water depths, ground conditions, how big the turbine the developer wants to use. So a lot of the time for concept, we do a lot of trial and error. So we'll look at a lot of different turbine sizes. We'll look at different foundation types to kind of see what works and what passes and what is the best. And I suppose the cost as well, like you could use a monopile, but it might actually end up being more costly than sometimes maybe using a jacket. A big factor here as well is not just the structure, but actually whether you use piles. A lot of issues is like hitting rock. So you have to do drilling grout, which is no one's a big fan of because it costs a lot of money, and there's only a few sites in the world that's been done. Another issue which has been happening in actually Taiwan and Japan is pile run. So these is where monopiles are being basically installed, and they go to look the next day and it's gone. So where it's basically sunk into the seabed. So it's because you're dealing with a lot of sand and clays, and it's really hard to, they're doing one or two bore, but like for a lot of sites, they just do one borehole with some CPD data, but the area covered is huge. So yeah, there's lots of challenges being in terms of even what to use. Yeah, so that's kind of what we do and kind of the life cycle. So a lot of our projects can last, if we're involved from the start to the end, it can be actually a 10-year period. So one of our projects at the moment, it's operational now, but it's still ongoing. We're looking at getting the certifications to make sure that everything, when it was installed, obviously things don't go to plan. So it was kind of looking at to make sure the structure integrity and all that is signed off, and then going into the operational. So all that information is captured. So when upgrades or when the structural assessments need to be done, that all that information is there. Okay. So this, I just thought it'd be useful to kind of give an overview of what I know. I was talking about a jacket, but it looks like kind of like a pylon, I suppose. So it looks like a fairly simple structure, but if you think about these structures are basically in some of the worst conditions. You're talking waves. Don't know how that has gone on. Anyways. You're talking waves. You have like J tubes, which have the cabling, boat landing. So like a lot of the boats need what they call CTVs. So they're the boats that come and maintain the turbines. And you have water, tide range variants. So you have to make sure, that they can safely get on that ladder and climb up between like ranges. Yeah, this is where at the top here is where the wind turbine kind of comes in, the tower and the braces. And I suppose the big challenge we have is obviously it's quite a hostile environment, but the challenge is to make these lighter and lighter because steel costs a lot of money, fabrication costs a lot of money. So the big challenge we have is I suppose that challenge between making a structure as optimized, as light as possible, but is that the best structure to be fabricated? Because you could have different you could have different sizes, for example. Oh, that's not going back, is it? There you could have different sizes, kind of legs here and braces, but then the welding of that might be difficult. It just the mass it's a production line per se, so that just might make it a lot more difficult at the fabrication yard. Also, for a lot of these jackets, they're going to be fabricated in different sites depending on the number. So you could have half of them being fabricated in Indonesia and half of them being fabricated in China. So it's it's quite a challenge in terms of like the skill, how they want to construct them horizontally, vertically. So it's a constant challenge, and we're kind of designing that sometimes without that end, without kind of having a fabricator on board. So yeah, it's quite challenging. Okay. Yeah, what else was I going to? Yeah, so I think, yeah, this is kind of, I suppose I thought be useful, the main kind of challenges I face on a day-to-day basis. And I think a big one is kind of the team. We work with developers, so it's kind of having that like fully integration team. Internally, we have a number of different teams structurally. We have what we deem primary steel, which is the big structural members, secondary steel, which is kind of the smaller boat landings, the internal platforms where kind of all the operations of the turbines need to go, and the J tubes, which carry the cables. Then we also have the geotech team, which, you know, they're getting information. A lot of the time we're getting information, the surveys is still ongoing, and we're asked to do detailed design when we technically might not have all the geotechnical data, which is very, very difficult. So it's kind of balancing that risk of what we can do, but also trying to kind of optimize our design and produce the best product for the client. So yeah, it's it's every day can be different at the moment as well. Like, you're looking at turbines, sometimes turbines will change if they don't haven't that agreed. So yeah, there's a lot of change even when you're in like a detailed design phase of a project. It's constant change. So it's always keeping us on our toes. But I think a big part of that is kind of having that really good relationship with the client, and being able to kind of, I suppose, have those honest conversations, and potentially the impact that the long term will have on the project, and what's their priority. You know, is it to get constructed by 2030? Is it to come in with the cheapest, or I should say cheap, the most value for money, I shouldn't say cheap, most competitive cost as well? Because, you know, when we're designing, and I suppose why they're pushing us, you know, to design something as optimized as possible, is because when they go into their auction rounds, that strike price, and that they're trying to be competitive as possible to get that backing, and to be awarded that contract for difference, so they can go to market. So it's really, you know, pushing that bounds with the information we have and have available at the time. Yeah, I think I covered a lot there. Another big one actually, which is beginning to cut, and I know a lot of problem is the supply chains. So these jackets are getting bigger. We're designing jackets in more than 100 meters water depth at the moment, 70. So we need bigger barges, bigger vessels to install them. As I said, the turbines are getting bigger, so we need the turbines need to be installed, getting them to market, getting them out to these sites. And also, it's not like a normal site. You're building these in the middle of the sea, so there's only windows where you can do this, only windows where you can install the piles, install the jackets. So you're really limited in kind of the constraints in terms of construction and installation as well. Yeah, really limited weather windows, and I suppose these weather windows affect the surveys actually as well. But yeah, which all kind of has the supply, backs up the supply chain, and as mentioned, all those targets, and, you know, from various people at the start, it's, if we want to construct and produce all this wind power, we need the supply chain, and at the moment that's a huge limitation, and that's the high demand, and when there's demand, cost goes up. So it's all about trying to bring that cost down where possible as well. Right, I think that's pretty much it. So yeah, thanks everyone. Thanks for listening, and yeah, any questions?